Alright, so what I'd like to do today is talk about some not programming stuff, though we'll try to tie it back maybe a little bit. I want to talk about logic some more, and then I want to talk about a concept called framing, which is very philosophical, of course. Let me fix all my pens. There we go. Okay, so yeah, what I want to start with today are two different concepts. One's called deduction, and the other is called induction. There are two different ways of approaching a problem and thinking about it. So, two different ways to make an argument, too. Make a deductive argument, make an inductive argument. So computers are really, really good at this concept called deduction, which is going to be a lot of like putting stuff together just in the right way, and everything goes through and it's fine and there's no ambiguity. So that's deduction in a nutshell. And then induction is something that humans are really good at that computers are not so good at, because it involves like thinking and like finding patterns and not so much hard and fast rules anywhere. So let's talk about both. Yeah, these are different kinds of arguments, and so I'm going to teach you like what makes an argument correct. Though we've talked about that already a little bit. We'll talk about it some more today, so I'll try and answer that in these little subsections of slides. So, okay, let's talk about both of those. What's deduction and what is induction? So, first of all, let's talk about an argument, because these are kinds of arguments. You can think of it as ways of reasoning or ways of arguing something. So, what is an argument made up of? It's got two pieces in general. When you make an argument to somebody, there are two pieces, right? There are premises, or premises, however you want to pronounce that, and a conclusion. So there's a bunch of premises in your argument, and they're all trying to give firepower towards your conclusion, right? Premise is a fancy word for assumption, so it kind of goes back to that question that I gave you in class when we were talking about assumptions of like something about a certain party thinking some way and like having to tie back things. There were premises, and they were supposed to argue for the conclusion, right? So here's kind of what an argument looks like. You got premise 1, you're assuming this thing. You got premise 2, some other cloud of an idea. You're assuming this thing. You got premise 3, you're assuming that thing. And they're all trying to be used as firepower to conclude some final conclusion. All right? And that is, here's your conclusion. Conclusion. So this is kind of what any argument in general is about. You have all these premises that you're assuming. Assume all these things are true, and under all those assumptions, this conclusion is what I'm trying to prove to you. All right? That's the idea. So that's what an argument in general is about. It's got assumptions and a conclusion. Premises mean assumptions. And a deductive argument, an argument we say is deductive when the conclusion is a certainty, if you are to assume those premises are true. So assuming all these premises are true, the conclusion must always be true. Very Kantian, right? The conclusion must always be true if the assumptions are true, right? That's what it means to be a deductive argument, when the conclusion is a certainty based on those assumptions. All right, so here is like a deductive argument example. They got some premises and a conclusion, so these two are like being used to generate the conclusion in some way. Otherwise, why would you say them? So, all right, the premises are the following. Premise 1. Assume that it's sunny in Fresno. It's definitely not true today, but just assume. Like pretend that we're in a universe where this is true right now. You get to assume all the assumptions. Premise 1, it's sunny in Fresno, so assume that. And then assume that premise 2 is also true. Assume that if it's sunny in Fresno, then I won't be carrying an umbrella. All right? So those are your two premises, and we're trying to use those to argue. Here's our conclusion. This is what we're trying to show. So, therefore, Lawton won't be carrying an umbrella. Okay? So that is a deductive argument. Do you see how it makes sense? If you assume both of these things are true, like, it's a big if, right? Because it is rainy today. But under these assumptions, if this is true, and you assume that, and if this is true and you assume that, do you see how you can plug in the idea, like it is sunny in Fresno, so I can conclude this thing, and I can plop out that thing for my conclusion. Does that make enough sense? That's what it means to be a deductive argument. Under those assumptions, the conclusion really is always true, right? If you're assuming this is like, these two words, these two premises are law. They're always true. So, you know that if it's sunny, I won't be carrying an umbrella, and you know that it's sunny, so you know that I won't be carrying an umbrella, right? And that's a deductive argument. Hopefully you see how those two premises are being used to generate the conclusion, right? conclusion must always be true if the premises are true. That's a deductive argument. The flip side of that is an inductive argument. Induction. There's also something in math, if you've taken a fancy math class like CSCI 26, there's something called mathematical induction that this is not. All right, that's a completely different use of the word induction, sadly. But inductive arguments, using induction, arguments can be inductive when the conclusion is not certain, but is very likely. So this is what humans are good at, computers are not good at. This is all about dealing with probabilities. Probabilities. That's the difference. Deduction is like just plug and chug, should always work out. Induction is like it should work out, should be true, should be very likely, right? So here's an inductive argument. Again, there's premises and a conclusion, just one premise this time, but here's the idea, right? You can see that this is not a certainty, but it's likely. So the premise, the assumption is every time I've walked by that dog over there, it hasn't tried to bite me, all right? So that is the premise, assume that. And so what can you conclude? With induction, you can conclude that, all right, the next time I walk by that dog, it probably won't try to bite me, right? Key word here is probably, yeah? Maybe if the dog had a really bad last 5 minutes, it will try to bite you next. But very, very likely, you're picking up on a pattern here, and you're concluding with inductive reasoning, what you expect to be true. Should be very likely that I am going to walk away without any wounds, okay? Any questions about the difference? See how that works? This is not a certainty. You can't conclude this. It's not always true if the dog's having a bad day, but it's very likely, and that's the difference between induction and deduction. Deduction, it better always be true. This should always work out if you assume these assumptions. Induction, it should usually be true. Very likely to be true that your conclusion works out based on assuming those premises. Okay. Any questions about that? So very high level, maybe a little vague, but that's the idea. All right, so let's talk about how to, deduction is what computers are good at. So let's zoom in on deduction, and let's talk about how to describe if a deductive argument is a good one or not, right? There are two adjectives you can use to describe a deductive argument. They're called valid and sound. So you can question the validity of an argument. You can question the soundness of a deductive argument. And soundness, by the way, is perfectly stronger. It's absolutely stronger than validity. So this is stronger than validity. You'd like your arguments to always be sound in general. Soundness implies validity first. You have to be valid in order to be sound, but we'll get to that, okay? So this is going to help us attack somebody's argument. We can say now, if I teach you these terms, you can be like, oh, your argument is not valid, it's invalid. Your argument is unsound. Haha, I'm right. So that's kind of what you can do. And I have come up with a cute little example of soundness. It has to do with the Muffin Man. And so I used ChatGPT to generate some like a backstory here. So let me read the backstory. But here's an argument, right? You've got two premises. You've got two premises and a conclusion going on here. You see the difference there? Premises, assume these things. Here's the conclusion again. But let me read to you my ChatGPT generated example. So in the quaint town of Deauville, renowned for its delightful bakeries, a peculiar incident unfolded that led to the arrest of an innocent citizen. So this is a bad argument on the screen right now. All right, the town was abuzz with the excitement over a mysterious theft of the mayor's prized golden muffin. Here's an artist recreation of the prized golden muffin that lives in the mayor's house. It's a priceless artifact handed down through generations of mayors of Deauville. All right, and so the cops, they received an anonymous tip suggesting that the Muffin Man, right, the jolly pastry chef, was the prime suspect in this heinous crime. And the tipster, who gave this tip to the cops, claimed to have witnessed the baker near the mayor's residence on the night of the theft. All right, so here is the argument that the prosecution used to lock away the Muffin Man. All right, assumption, fact one. Assume this is true. The golden muffin, it was stolen from the mayor's residence, right? That's a premise. That's a true thing. Also, the Muffin Man was seen near the mayor's residence on the night of the theft. Another assumption, another premise. That is a true thing. Using these both as firepower, the prosecution at the trial of the Muffin Man concluded, therefore, the Muffin Man must be the thief who stole the golden muffin and they locked him away. Is this a good argument? Should the Muffin Man have been locked away? Why not? Why could he be not proven guilty? Yes, some ideas. Both of you can answer in some order. Okay.
One eyewitness testimony, I believe, is the weakest form of
very good.
evidence.
Very good. Okay.
Mm-hmm. And second thing is that while yes, this is probably worth looking into further, there's not enough evidence to convict the Muffin Man just because he was in the general area of the mayor's residence.
Very good.
Anyone who lives on that block is within the general area of the mayor's residence.
That's a great point. Yeah. Are you also going to make a similar? Okay, nice. Any other ideas? Any other reasons why we should not have immediately put the Muffin Man behind bars? But yeah, that is the idea. This is circumstantial evidence, right? I'm not trying to teach law right now. I'm trying to teach arguments. So here are the arguments, and they're trying to be used. You're trying to combine these facts together and somehow conclude with beyond a shadow of a doubt, right? Because that's what you have to prove to a jury. You have to conclude that both of these things together mean that the Muffin Man must have been the thief who stole the golden muffin. But there's really no way to combine these and conclude this, right? It's not a certainty, right? Does that make sense? That's the goal there. So the issue with this argument is that it is invalid. That's a word that I'm going to teach you. All right, this is an invalid argument. You can't use these together to conclude this. It doesn't work out. All right, and just by being invalid, it's also unsound because soundness is stronger than validity. All right, so here's a better it's a different example. I think the muffin example is a cool one, but here's an example that ties us back to computer science. Here's another argument. All right, and I want you to see if you will agree with it as well. There's something wrong with this one now. So first of all, I want to say that this one is invalid. I'll teach you that term in a second. All right, this is another example argument. It's got two premises and a conclusion. So assume these things. First of all, it's going to talk about this website called GitHub. That is where I host the code from class. Just like all the cool kids who like to write code, they have GitHub accounts, and so a lot of people post their code that they wrote there. It's like social media for programmers in a sense. You can host your code there. But here are two assumptions, and here's a conclusion, right? Relevant to computer science. All people with GitHub accounts are successful programmers. Assume that, all right? And then assume that John has a GitHub account. And then the conclusion is, therefore, John is a successful programmer, all right? So if you were trying to, you're like a big tech company or hiring manager, would you hire John with this argument? Would you conclude that John is a successful programmer and he should totally be part of our company? Yes or no? I hear yes. I also see some head nods. Who would like to say something? Why yes or why no? Yeah. So this is an interesting fact. Do you see how you can combine, if you are assuming, right, if you are assuming that we live in a universe where both of those things are true, you really can, you can get out that John must be a successful programmer based on those assumptions. Yes? That's interesting. But still, would you hire John in real life? Why not? Yeah.
Because my grandmother can go and make a GitHub account.
Yes.
That doesn't mean she knows a lick about coding.
Exactly. So we take issue with this assumption. You see that? Under those assumptions, we can conclude the thing, and it works out. But we don't believe the assumptions. Maybe we do believe that John has a GitHub account because he told us his username. But we don't agree with this assumption, so this is questionable. And this is a valid argument. That's an example of a valid argument, but unsound. So that's why I'm going to teach you these terms now. Okay? So with that, hopefully those are some cool, colorful examples that are going to help you here. But here's essentially, here's the idea. Here's essentially what happens when you make an argument. It looks kind of like this. All right? It looks kind of like this. You got some premises and a conclusion. Some people like to draw a line between them. But usually, it kind of works in this way. Like you say something gives you something else, and you give the starting point, and you can kind of plug it in and get the conclusion. That's kind of usually what arguments look like in this form. But we say that an argument is valid if it's impossible for the premises to be true and the conclusion to be false. So another way to say that is like, yes, the premises, you really can plug things in, plug in the A to this, A implies B, and then you get out the B, and you really can conclude. Right? A valid argument is if you really assume you're in a universe where these premises are true, you can conclude the conclusion. All right? It does follow correctly. It's impossible for the premises to be true and the conclusion to be false. They do work out, they do combine together. That's what it means to be a valid argument. Right? So this is a valid argument. You see that? You really can combine these two. You can plug John into this statement, and you can get out that he must be a successful programmer. So that's fine. That's a valid argument. But a sound argument is one that must be valid to start with. An argument is sound if it's valid, and it's got to be valid first, and all the premises have to be true ideas. Okay? So this is valid, but it's not sound because we don't agree with this. This is not a true statement. You see that? If we're like playing a thought game or having a thought experiment, then sure, like it does follow, it's valid. But like this is not true in real life. So it's not a sound argument, right? And then this one broke down because it wasn't even valid. See that? Like there's no way to combine these two and get the third thing. It's not true for the, where am I? Premises to be true and the conclusion to be false. It is totally okay for the premises to be true and the conclusion to be false here. Because somebody else could have done it. When that person, that tipster, anonymous tipster, walked away. Maybe it was the tipster themselves. Who knows? So that's the idea, right? That's deductive arguments and the setup. An argument is valid if it's impossible for the premises to be true and the conclusion to be false. It does follow under those assumptions, even if we're assuming a weird universe. And a sound argument is one that's valid first, and then all the premises must be true. All right? So that's the idea. Any questions about these facts, these new terms? Talking about how to break down an argument, dash it down maybe. And if we're good, let's go to the ByClicker page. And I'll stop the attendance after this first one, so make sure to do attendance if you haven't already. But here's my first question for you. You can get into groups and talk about it together, of course. But here is my question for you. Is this a valid or sound argument? A, B, C, or D? Valid only, valid and sound or neither. Remember, here's what it means to be valid or sound. And here's the argument. Assume. These are your two assumptions, and then here's your conclusion, right? Assume that all birds can fly. Assume that bats are birds. Therefore, bats can fly is the conclusion, right? So tell me if it's valid, sound, both, or neither. Take a few minutes to discuss as a group. We'll talk about that. Yes, we can talk about that later. So, yeah, that's a good thought. What does it need to be valid? Do they follow, right? Mouse pointer's in the way there. Yeah, your questions are good questions. You're thinking the right stuff. Another 30 seconds or so. I see that our words are dying down. So another 30 seconds to get in your ideas. 5, 4, 3, 2, 1. All right, let's see what we're thinking. Ooh, look at us. All right, we're thinking A with a majority. We're thinking A. Interesting, interesting, interesting. Yeah, it is valid. Good. So can somebody tell me why it's valid? Yeah, sure.
So, if we were to assume that all birds can fly,
Yep.
and if we were to assume that bats are birds, then therefore the conclusion that bats can fly is valid.
You can plug bats into this idea. We're assuming we live in a universe where this is true, and we can plop out this conclusion. Does that make sense? That is, yeah, very good. This is why it's valid. We need to go and make it sound. If it's sound, it's valid. Like, we have that checked. But if it's sound, all the premises also need to be true. Are the premises true?
No.
Now, first of all, you got birds that can't fly, like penguins. And second of all, bats, surprisingly, are not birds. I had to look this up. Bats are mammals. Mammals are not birds. They're different classes of things. I'm not a biologist. But both of these are incorrect assumptions. But if, again, we assumed we lived in a universe where both of these were true, it is a valid argument. And that's all it means to be valid. Just under these assumptions, we can get the conclusion. Okay?
However, we live in a universe where bats can fly regardless of this.
Yeah, so it was a weird argument. Yeah, exactly. So this is a little tricky, but you're getting it. All right, here's another one. I'll start again. Valid or sound? Here's your argument. Assume all snakes are reptiles, all lizards are reptiles, therefore all snakes are lizards. It's another argument. Two premises and a conclusion. You tell me. I won't give you as long this time, though. Let me hide the results. Take a minute to discuss. Oh, sorry. Let me give you this too here. Seems wrong, right? So you can tell me why, though. You have the tools now to tell me why it's a bad argument. All right, another few seconds. 10 more seconds to get an answer. All right, let's see. Ooh, look at us. We are not so sure. I don't think we have a majority even. Yeah, not a majority, but most of us are thinking D. So, your option is never B, right? First of all, option can never be B. In order to be sound, it must also be valid. So you can never have an answer of B. We gotta first see if it's valid, because that would give us the final say, right? So if it's valid, we need to somehow be able to combine these two facts and get out that all snakes are lizards. Can we combine them in some way? Can we plug something into something else? Like snakes into this, lizards into that? Not really, right? What we can conclude, like it was no use saying this, but if you wanted to, you can conclude, therefore, all snakes are reptiles. We're saying stuff about reptiles, not about what makes a snake or what makes a lizard. It's kind of backwards, right? That's the idea. It's kind of like we have snake. You can go from snake to reptile. That's kind of what the first one's saying. And you can go from lizard to reptile. You can't go backwards. You see how the arrow is only one direction? Like, you give me a snake, I can tell you that it's a reptile. That's what this first thing is saying. You give me a lizard, I'm telling you that it's a reptile. But you can't go backwards. All right? To like rerun it in some different way. So there's no way to combine the two. Like, it doesn't work out. Like, doesn't make sense. Okay, so that means it's not valid. And so if it's not valid, it can't be any of these, and so the answer is in fact D. Does that make sense to us? Seemed to confuse us, this argument. But D is the right answer. Do we see it now? Yell at me if you have questions. But this is the idea. I have two more of these because this is such a cool, interesting thing. So here's another one. Put it up here. So here is the argument. This is an interesting one. So every time Dave orders pizza, his neighbor, Bob, can smell it from his house. All right, so let's assume that, assumption one. And assume that Bob smells pizza right now. Therefore, conclusion, Dave must have ordered pizza. Let me rerun this question, sorry. There you go. Now you can enter in your new answer. I won't give you as long this time, but think about it. Discuss with your neighbor. Under these two assumptions, can you conclude this? Is it valid? Is it sound? We know it can't just be sound now. So B is never an option. We got three others. Remember, for valid, it needs to be that the premises imply the conclusion. It follows all the time. It always works out. All right, I'll give you 15 more seconds to get your best guess in.
Is it impossible for the premises to be true? Is it impossible? Yes. Or no? It's possible.
All right, that's as much time as I want to give you. And we are very confused about this one. Look at us. So this is why I'm asking these things. This is why we're learning right now. This is new stuff, right? This is why you're in this class. So, okay, we got two premises going on here, and let's break it down. So every time Dave orders pizza, his neighbor Bob can smell it from his house. So essentially it's like Dave orders pizza. You can go from there to Bob can smell it, right? Bob smells pizza. See that? That's the direction for that arrow in this idea, right? You give me this, you tell me that Dave ordered pizza, totally Bob is going to smell it. That's what it's saying, right? In symbol kind of form. This one's saying that Bob smells pizza right now. Can you plug Bob into this other thing and conclude that Dave must have ordered pizza?
You can. Yes.
You can't. You can't because the arrow's the wrong way. That would be trying to run this arrow backwards. That's not what the assumption's saying. Do you see that? It's saying, you give me that this is true, I'll show you that this is true. I'll have a reason. If Dave orders pizza, then Bob smells pizza. It's not saying that if Bob smells pizza, then Dave ordered that pizza. Maybe it was a different neighbor. Does that make sense? That's the issue here. You're trying to run it backwards. This is an incorrect conclusion because you're trying to run this idea backwards. It's not true that it's not saying this, right? It's not going from Bob smells pizza, therefore Dave must have ordered pizza. It's not what it's saying. It's saying the other way. If Dave ordered pizza, then Bob must be able to smell it. Okay? Could have been a different neighbor, so it's an invalid argument, which means it's neither. Any questions about that? That was confusing, I know. Yeah.
Wouldn't this conclusion be inductive?
Yes, but valid and soundness have to do with deductive arguments only. Yeah. This is an inductive idea, like, we shouldn't have said must. Dave probably ordered pizza. That would be like an inductive argument, I would say. You could run it backwards in induction. But you have to say that it might not be true. Okay? Good ideas. Any thoughts? Any other last thoughts or comments about this one? I have one more. One more question for us. All right. Here's your argument. Two assumptions and a conclusion again. Assume all mammals are warm-blooded animals. Assume dolphins are mammals. Therefore, conclusion, dolphins are warm-blooded animals. Oh, and sorry, let me give you the definitions one more time. There they are. All right, a few more seconds. Is this a valid argument? Is it a sound argument? You know they have to go hand in hand, right? If it's can't just be sound. So B is always off the table. Or is it none of that? 5, 4, 3, 2, 1. All right, let's see. Nice. We seem to have reached a conclusion. And we think this is valid and sound. Yes, yes it is. Good job. We're getting it now, I think. So do you see how this one's saying, you give me a mammal, I'll tell you that it's a warm-blooded animal? It's kind of what it's saying. Warm-blooded. And then alright, dolphin is a mammal. You know that. So you can plug dolphin into this idea. You can follow the arrow to get out that dolphins must be warm-blooded animals. So you can conclude it. It does work out. Does that make sense? So it's a valid argument for sure. So, okay. Now it's sound too because these are valid things. Or not valid. These are correct, true assumptions, yeah? Mammals are warm-blooded animals. That is a true thing. True thing to say. Reptiles are not mammals, and I know that's not true for them. And then dolphins are mammals. Those are two true assumptions. They do work together to conclude, to make the conclusion a thing. It does. The conclusion does follow from the premises. It's always going to work out. So it's valid, and then also the conclusion that the premises are true, so it is sound. It's a sound argument, valid and sound. Any questions about that? So yeah, now you can knock down people's argument. You can be like, no, this is invalid, doesn't make sense. Or you can say it's not sound. You're like, you're assuming some weird universe right now. It's not our universe. Okay? So that's why we're learning that. It's fun stuff. And I want to take a second now to zoom out and talk about this arrow, because this arrow was everywhere. It came up, right? There's a word for that. It's called implication. It's an if statement. We're going back to logic now, right? So again, English is ambiguous. We want to make a logical language so that we never have to have ambiguities ever again. Everybody can understand everybody else. Let's try to figure out what if means. Let's try to make a logical symbol for if. It is that arrow, all right? So here's the secret. Let's make a truth table for if. So here's a statement. We'd like to say if it's true or false, right? I'd like to see if Dad is lying to us or not. So Dad says, I'll give you $20 if you mow the lawn. So do you see how this is an if idea, an if statement? If you mow the lawn, Dad says, then I'll give you $20. There's an arrow in that direction. See that? You give me that, I'll give you that. And again, we're going to try and figure out what it means for this to be true or false, this statement to be true or false. And false is all about were we lied to. Okay, false. You were lied to. So under which conditions of us mowing the lawn and getting $20, all the possibilities, under which combinations of those did Dad totally lie to us? Because that's what it means for this if to be false. All right? Under what conditions would we feel cheated if we didn't get that $20? All right? So here's the idea. If you mow the lawn, then I'll give you $20. What Dad is saying, the arrow's going in that direction. And then here are all the options of mowing the lawn and getting $20. See that? True, false, like all those things. You mowed the lawn and you got $20. You mowed the lawn and you didn't get $20, etc., etc. Okay? And the question is, which of these combinations did Dad lie to you? All right? If you mow the lawn and you got the $20, did Dad lie when he said this? No. You actually got what you wanted. It worked out. All right, let's skip the second one because that's the important one. What about this one? If you didn't mow the lawn but you got $20 anyway, did Dad lie to you?
Yeah.
No. You got $20 for free. We don't even know if Dad lied to us or not. He was just nice to us that day. We didn't do the work, but we still got the money. We don't feel cheated at all. Dad did not lie to us. Does that make sense? So a few of us said that he lied. That's not true. And one last time, if we mow the lawn and we didn't, if we didn't mow the lawn and we didn't get $20, was Dad lying when he said this to us? No, we didn't uphold our end of the bargain. Of course we're not getting $20. That's totally fine to be in this universe. In this universe, it's also fine, right? If we didn't uphold our end of the bargain, then anything goes. It doesn't matter what happens here, right? So you didn't do the work, so you don't feel cheated. This is the one time, do you see, that Dad lied to you. If you did mow the lawn and you did not get $20, true and false, then Dad really did lie. Because he said, I'll give you $20 if you mow the lawn. If you mow the lawn, then I'll give you $20. We did mow the lawn, but we did not get $20. So we feel cheated, Dad lied to us, and we'll never try to mow the lawn again now. Okay? So this is the one case where it is not right. This is like the false case. Does that make sense? It's the one weird one. Every other idea makes sense to us. So that's our new symbol. It's called implication. It's like if something, then something. If A, then B. All right? So it's like if A is true, then B is true. That's kind of a mathematical way of saying this. If A is true, then B is true. Okay? And the arrow, it's like an arrow or a double arrow, depending on how you want to write it. This is the symbol for implication. You have the hypothesis, the if side on this side, and then the then side, the thing that you're trying to conclude on the right. Right? So an implication, it's the logical term for an if-then statement in math. And in programming, we call it a conditional. We talked about that in Scratch. So we just discovered the truth table for implication. And also, we can figure out, we know how to prove it too now. Okay? So here are your options. Here's A implies B. If A, you can read it like this. If A, then B. Right? That's how we're going to write it in math now. It's our arrow. If you do this, then I'll do this. Okay? That's the idea. So, again, it'd be like A can be mowed the lawn, right? Because this is our argument. If you mowed the lawn, then you're getting $20. That's what Dad is saying. Mowed lawn, got $20. That's what B could be. So the implication, here's its truth table. There's only one way to make it false, right? There's only one way to make it false. It's if you upheld your hypothesis. You did the if part, but you didn't get the then part, right? That's the one way to make it false. That's the one way you were lied to. Does that make sense? That's what it means. So every other time it's true, right? It's true if you upheld your end of the bargain, you mowed the lawn, you got $20, Dad didn't lie. So that was a true statement. And in every other case, when you didn't uphold your end of the bargain, anything goes. Nothing matters at that point. You didn't actually mow the lawn at that point. So it's still, Dad didn't lie to you in that case either. Okay? So it's true everywhere, but in this third case. All right? So that is a mathematical if-then statement. It's called implication. And that actually, now if you go back to these, it might make a little bit more sense now as well. But yeah, another way to say it is like, if I give you A, then you have to give me B. It's kind of how it's shown. And then the way to prove, if you have an implication, you're like, I'm proving that it's true. I want to prove to you that this idea is true, that I'm not lying to you. Well, then what does that mean? You just have to show that it's impossible to be in this case, right? Because every other case is true. You got to show that it's impossible to have the if part, fulfill your hypothesis, and then not receive this one, right? You got to make sure that you can never get to this one case right here. That's the one that you have to cross off. That's how you prove it. Because that means if you've shown that you're not in this case, crossed it off, then you're in any of the other cases, and that's true at that point. Okay? So that's more symbol pushing. That might be a little vague, but that's the idea. Any questions about that? So let's go back to deduction. Dun, dun, dun. This is, by the way, like when you take a philosophy class and you learn about deduction, this is like the quintessential deductive argument. This is the one that everybody uses. This is a valid argument, right? It's also a sound argument, I believe, assuming that we believe that Socrates really existed. So here's your idea. Here's the deductive argument. So assume that all men are mortal. Assume that Socrates is a man. Therefore, Socrates is mortal. So this is a valid argument for sure, right? You can plug Socrates into this idea because Socrates is a man. Get out that he was mortal. Okay? But again, dun, 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 you can think of it like this, the way I was drawing our examples. This argument, it's valid because essentially this first line is saying, if man, then mortal. Man implies mortal. You see that? If man, then mortal. than mortal. And that's like your A and your B from the previous slide. And it's like, assume this is true. Assume this is true. Assume that man is also true. You've got a man somewhere. Then you can plug the man into this implication and get out that mortal must have been true. Right? Therefore, mortal is true. Right? So this is the argument in symbol form. And we can use this truth table now that we know what it means for implication to be true and assume that it's true. We can use that as firepower. Right? So assume this conclusion works out really because of this. Right? Assume that this is true. Assume that we're like man implies mortal. So assume that this is true. Right? So assume that we're in one of these cases, right? Because we're assuming that it's true. Let me use a different color maybe. I'll undo it later. So assume we're in either, right? We're assuming this is true, so we're either in this one, or this one of the rainbow cases. That's the idea. So maybe I'll put there, one of these bulleted ones. Because that's what we're assuming, right? We're assuming that this implication is true. There's only 3 ways to make it true. It must be in one of these. Does that make sense? So it's already crossed off this idea. That can't be true now. Then, all right, assume that man is true. That's the A part. That's the hypothesis. Assume that we're in the universe where this is true. So look at how some of these, where the answer is some of these options here, they have it where A is false, where the hypothesis is false. We don't care about those anymore because we're assuming that the hypothesis part is true, the if part is true. So we've crossed off these too now. See that? So now we're only in this case. See that? We must only be in this case now based on our assumptions. And what can we conclude? We're trying to say always, beyond a shadow of a doubt, that the B part, the conclusion, is always true. Yeah, it must have been true. That's the only case, right? That's what's true about B. We've crossed off everything else. That must be really true. We can read it off the table at that point, right? Does that make any sense at all? That's kind of the argument. That's why it's valid. That's how you prove validity under an implication. Okay? That's the secret. And so, if you stare at it long enough, go back, rewatch the video or something. It's still a little confusing. But really, it's true that the conclusion here follows from the truth table. You've crossed off which universe you're in, the truth table for implication. Okay? That's the idea. So, yeah, that's deduction. That's why it works. That's what it means to be valid. And hopefully that makes a little bit more sense. Any questions about that? That's our mathematical if-then statement. All right. One last place I'm going with this. Now that we have a truth table, we have a logical operation here. Implication. It's a new thing. Can you make a circuit diagram for it? Sure you can. Because I told you that anything, right? Any column of a truth table, you can make it for sure using ands, ors, and nots, in addition to some other cool ones. So, this is equivalent, in fact, actually to something else. It's equivalent to not A ORed with B. Those are the same idea. That's what it means to be implication. It's the same as not A or B. A implies B is the same as that. If A, then B is the same as not A or B. Now, let me show that to you. The way that I'll prove it to you is that I'm going to fill this in, and it's going to be the exact same as this, so it works out in every case. It always matches it. That means they're equivalent, right? So not A or B, what do I put in here? So A is true, so not A is false. Ored, though, with true still. B is true. The answer is true. Cool. Checks out. And then here, not A or B. Not A is false. Ored with another false. That's the only way to make the final or false, right? I'm oring false with false. False, ored with false. So I'm negating the A part. And that really is false. Cool. And then finally, not A ored with B. In either of these cases, you see that A is false. So not A is true in both of these cases. You're oring true with anything. Still true. So true, true. So you can totally make a circuit now that takes two things. Use these not gates and an OR gate. Take in your A, take in your B. You can make a computer now that checks if your implication was true. You just fill in what happened. Do some fancy logic gate stuff, and then you can plop out the answer of A implies B now. Because you can use a not gate and an OR gate. That's pretty cool. So you can make a computer do that result with some circuitry. Are we good with that? So that's a lot. Deductive arguments, the idea of implication, an if-then statement, making sure it's not ambiguous. We made a truth table for it. and we're off to the races. Okay, that's the idea there. So, if we're happy in the remaining time, I want to talk about a couple different concepts that aren't strictly related, but they're close. They're still kind of philosophical. I thought it was funny because I named it wrong. It's called framing, the next topic, but I said farming the first time, and so I'm just going to keep that forever now. But framing is what I want to talk to you about now. And this is a very quick idea that I'm sure you've run into before. I just want to spell it out because this class is about arguments, and sometimes your arguments aren't going to get through to people. All right? It's like, I'm going to try and answer this. Why can't this person who I'm arguing with see my point? I'm so right now. It's so obvious that I am in the right. What is wrong? And so it has to do with a frame of reference, the frame of reference that somebody holds, right? That's how somebody views a situation, right? Let's see here. Your frame of reference, when you are thinking about anything, it shapes how you view the world, right? You have some thoughts in your mind that really are unwavering. You have a way of viewing the world, right? And that also influences the assumptions that you're willing to make. So for some people, it's a sound argument, but for some other people, it's only a valid argument because they don't assume those things. Okay, that's interesting. So another way to describe this frame of reference, it's a synonym for it is your worldview. Your worldview is not the same as somebody else's, most likely. Okay, and it all has to do about the connotations of words as well. Connotations, not the denotations. So you're arguing something. It's all about the nitty-gritty now, the connotations of words, and somebody's worldview influences whether or not they're going to agree with you, right? So let's see here. Let me read these and I'll give you this fun table that I found. So if, by the way, you can control the other person's frame of reference, you can influence their worldview, you can very often get them to believe whatever you want them to believe at that point. All right? So that's one thing. That's how you get brainwashed. And then what I'm trying to say here with this slide is that somebody can think the exact opposite thing as you. Like you think you're right, they can think they're right too because of their worldview. It's completely different than yours. They can also justify it a lot of the time too, which is disgusting when you think one thing and they think another. But here's the idea. I'm sure you've heard these before, but let's talk about politics because that's the easiest place to go here. Here are different frames of reference for politics. Usually you've got people on the left, people on the right. And so here is the same idea explained differently with different thoughts behind it, right? So just read this table a little while and see, have you heard people say these terms? Have you heard them, like you might think one way, have you heard other people think the other way? And do you see that using these terms, it kind of like changes everything, right? Does that make sense to us? If you were to change the frame of reference, you would change like from one phrase to another. Do you see the implications behind that, the connotations behind those words? Like it's the same idea, but just explained completely differently, and that influences the way that somebody's going to think about a topic, which is unfortunate a lot of the time, especially in politics. So obviously these are very simplified ideas, but I'm sure you've seen this before. So that's what it means to be a frame of reference, right? If you can control this, you can have somebody think your way, then you can usually control the argument too. So that's unfortunate. And also maybe a little cool, but that's the reason why some people, like, you think you're doing a great job, you got a great sound argument, somebody doesn't believe that it's sound at the same time, maybe. Okay, that's what I wanted to say about that, because while we're on the subject of arguments. And then I want to talk about something completely different now in the remaining time. It's called a state machine, and it's really, really fancy. It has to do with computation. I guess it has arrows involved, so maybe that's why I put it in these slides. But it's all about making algorithms, right? So it's all about breaking down the process of computation to do something for you. So technically this is a mini programming lecture that's just not Scratch. It's a bit more generic than that. So we kind of know how to break down a process, how to break down a computation these days. Like you'll invent an algorithm, right? We've been talking about this. You've got to invent your own algorithms to do stuff for assignments, right? And you had to like make little bite-sized pieces to like get some of the way there, some more of the way there, some more of the way there, until you're at the thing you wanted. Yeah? That's how computation works. That's how computer programs work. And so I'm going to teach you a method that has to do with breaking down computation into a way. If you can build a state machine from what I'm asking you to do, if you can find a state machine in your problem, usually you can make a really good answer out of it. All right, so let me teach you what it means to be a state machine. It's just a bunch of circles and arrows, first of all, but you can program these, and it makes it very, very obvious about like what's correct and what's not, what's going to happen, what's not going to happen. All right, so in a state machine, by the way, you have a bunch of circles and arrows. So first of all, you got bunches of circles and arrows, and every circle is a state. All right, you're always in some state. That's the first idea of a state machine. And then you can move around between states using the arrows, and the arrows are called transitions. They take you to different places. All right, so here's like a silly state machine. What they do, though, is they abstract over some process, maybe a real life thing, maybe a computational thing. All right, so here's a state machine for a very, very boring person. And let's say that they only have 3 states in their life. They have the work state, the home state, and the bed state. All right. There's always a concept of where you start out. Maybe when you're born at home. So like there's an arrow coming in to nowhere. That's called your starting state, your start state, initial state. So you start your life in the home state. And then here is kind of what the state machine is saying. This is how you can move around. All right. So maybe you're at the home state, but it's time to go to work. And so you want to get to the work state. And so you're forced to take the train. See that? The only way to get from the home state to the work state is to take the train. Does that make sense? And so if you like program this, do you see how like you're enforcing the fact that you must have taken the train in order to get to the work state? Like you're saying what is allowable. So that's a very powerful idea. And then maybe you go to work and then it's time to go home. So you're going to take the train back to get back to your home state. Does that make sense? So the only way you got back to home from work was this transition. So it's a very powerful idea. And if you code that up. And then, all right, you have dinner. Then you want to go to the bed state. And the only way to get there is to follow the sleep transition to get to the bed state. Does that make sense? Then once you wake up, you're going to follow the wake transition from the bed state to take you back to the home state. And maybe it's time for work again now. And so you can follow these in any order. You see how like there's like it's baked in the idea of like, okay, maybe you come back home for lunch or something. And you go back to work before going to sleep again. Or maybe it's the weekend, like you stay at home and you go into bed twice before you go back to work. Those are all allowable by the state machine, but it's important because it's spelling out exactly what you can do, which says a lot about what you can't do as well. So it makes for a very easy program to write. And so that's a simple state machine. Here's a more complicated state machine. This is like for, I stole this from the internet. It's like for a Lyft app or an Uber app, like a ride-sharing app. This is kind of how the app works. So you can program it using a state machine. So let's say that you start in this state. That's kind of what it's saying there. So you're on your Uber app and you request a trip from somebody. So the app takes you into the trip requested mode. And then before, like you want to get to the driver assigned state because you want to like have somebody pick you up. But the Uber app, what it's doing is it needs to process your payment first. It needs to go to the payment state. Okay, so it's going to request the payment right after you request your trip. Okay, so then you're going to go to the payment state. That's what the app is doing. And that's checking your credit card, right? If it fails, you got to go and re-request your trip after putting in a new credit card. Do you see that? Only if you follow the payment success transition does a driver get assigned to you and you'll actually be picked up at that point. Do you see how writing this state machine is very clear that the only way to get a trip, only way to get in a car is to have your credit card work? See that? So it's a very powerful idea. Like if you program this, it's guaranteed if your program matches the state machine that you're never going to get a free ride. And that's what the app developers want for sure, right? There's only one way to get to the driver assigned state. You must go through the payment success transition. See that? It's a very powerful idea. And then like you get in the car, the driver could cancel on you, then you have to re-request the trip. That's a possibility. Or you get picked up, and then the trip complete is, like the trip is over, and then the driver goes back to an unassigned state, and then like there's some cleanup in the program probably. You got to go between that to a trip end state. But that's the idea. If you could program this, and that's what the app developers are probably doing, do you see how it's very easy to prove that there's no way to get to this state before having gone through the payment state? That's a very powerful thing, and it's just you can just read it off of the state machine. So that it's a simple idea, but it's very, very powerful. It says exactly what you must be able to do and the ways that you can do it. Okay? So that's a state machine. If you're building a state machine yourself, here's how you do it. You group your idea, your program, into different states that you could be in and actions that move you around between those states. All right. So here's another simple, silly idea. Let's make a state machine for you, the student in this class. So let's say that as a student, I think of you as a two-state machine. You've got two states. You have a learn state and you have a practice state. All right. So those are your two states: a learn state and a practice state. And your initial state, by the way, is the learn state. So I'll draw an arrow to indicate that. Your starting state in this class, like I haven't given you any homework yet on the first day of class, so I made you start learning first. Right? So that was your starting state. And then you alternate between those states when things get posted or assigned. Like if I assign an assignment, you go from the learn state into the practice state. If you finish your assignment and it's time for lecture again, you go from the practice state to the learn state. And as long as you're not done, you can stay in the same state. You can have a transition that keeps you there. The lecture's not over, you're still learning. If the assignment's not finished, you're still practicing. Yeah. So that's kind of how you work as a student. And you can stay in the same state as long as you need to. And then you just like move around between it. And that's like how you can model yourself maybe in this class. There's also a concept of a ending state. You can mark that the program must end in this particular state or these particular states, and you put like a double circle for those. These are called final states. Your final state in this class is the practice state, because at the end of class, right, there's nothing left for me to teach you, and you just take the final exam and you leave. The final exam is a practice event. Yeah, so that's where you end as a student. You're going to end on this state rather than the learn state. Okay, so that's a state machine in a nutshell. Are there any questions about that? Just very generic ideas, but if you can program this, and I'll show you that one day, if you can program this, it makes for a very easily provable program. Like, I know that this is going to happen in this order. I must go through here to get to here. Stuff like that. Okay? So it's a really cool idea, and let me show you on paper a really cool state machine. I learned this in my first programming class at Fresno State, so I'm going to teach it to you now. We're going to count the words in a sentence with a state machine. All right? So let's say that we got a sentence from the user, all right? Maybe we got it in Scratch, so it's sitting in the answer variable. Maybe the user typed a sentence. Do you see how it's, first of all, do you understand that it's not obvious? It's not easy to check how many words were in this sentence that the user typed, whatever it was, because they could have, like, tricked you or tried to trick you. Like, imagine, like, one obvious solution might be like, oh, just count the spaces, right? Add 1 to that, and that's how many words there were, because words separate spaces. You can't really bank on that, because what if the user's answer was trying to trick you and they started like with 3 spaces, and then they said their sentence like, hi, space, mom, or something, and that was their exclamation point, and then another space at the end of that. Because if you just counted spaces, and that's like an obvious idea, it wouldn't give you the right number of words. There's only really 2 words in this sentence. So we need to do something fancier, and a state machine is going to do it for us and make it very easy to find the right answer. All right, so here's the secret. We're going to build a state machine that reads the characters of the sentence one by one. So we're going to look at this one first, then this one, then this one, then this one. We're going to look at them all in order from left to right, and we're going to keep track of whether or not they were white space characters. So it could have been like a tab, could have been an enter. We'll count that as spacing. That's called a white space character in computer science, but I just have spaces in this example. But the secret is, the thing that's going to influence our state machine is that white space separates words. It really does, but there might be a lot of spaces, so we'll have to account for that somehow in our state machine. And then also the other key idea is that every character you see is either part of an old word, one that you've already started reading, or it's the start of a new word. All right? And the state machine is going to show that to us. All right? We'll also need a variable. We'll keep track of that in a second. All right? We're going to need a count variable starting at 0 to count all our words. Okay? We're going to start off our count variable, and eventually we want it to become 2 after we run our state machine through the sentence. Okay? So let me show you the secret. Here is the state machine. All right? It's a 2-state machine to count the words in a sentence. You're either inside of a word or outside of a word. All right? That's how I want to explain it. Those are the 2 states that you can be in. Either you're outside a word, or you're inside a word. Those are your 2 states. And you're going to read all these characters in a sentence and like move around between these 2 states. Right? What's the starting state? Before you've read anything, are we inside of a word or outside of a word? We haven't read any words, right? So you're totally outside of a word at the start, and then you run. All right? So, okay, let's think about this. If you're outside of a word and you see, for example, a space character, are you inside of a word now? No, you're still outside of a word. So if you see a space, you're still outside. All right, so that's fine. What means, so you're still outside. You see the H though, and you're outside of a word, you're now inside of one, yeah? See that? So you see a non-space character when you were outside, now you're inside of one. See a non-space character. So now I saw the H, now I'm inside of a word. And now if you're still inside of a word and you see another character that's not a space, you stay there, right? You're still inside of that same word. Does that make sense to you? If you see a non-space character, you're still, like the I after the H, you're still inside of a word. Because that's not a space character, because spaces take you outside, yeah? But if you were inside, you saw the H, you saw the I, now you see a space, you were inside of a word, but the space is outside. See that? So we're just building the state machine. I haven't told you how to count yet. I'll take you back to the outside of the word state if you see a space character. So that is the state machine. And now this is going to count words for us. Because what we want to do is we want to take this count variable, start it at 0, and we want to increment it every time we see a new word. Does anybody see a transition, one of these guys, like these arrows, that notices when we found a brand new word? Yeah, which one? The top one. Good. Do you see that this is a very interesting and important transition? When you are outside of a word and you saw a non-space character, you're inside of a word now. You transition to there. And that was the first time you saw that new word. See how that's discovering a brand new word? That transition when you follow it? I'll walk through this example and I'll make it very obvious. But that's the secret. If you are here, you're not in a word right now. You're looking for new ones. You notice a new one the second you see a non-space character, the second you see that H. That starts a word. That will take you from outside to inside. And you don't want to double count it, so you don't want to count more over here when you're already inside of a word. Just the first character of that new word, add 1 to your count. That's going to be the secret. All right? That's the goal. So, all right. Let's run this idea now. Let me make an arrow so I can just keep reusing the arrow with my mouse. So let's run this sentence through the state machine. We'll keep track of count. Count starts at 0. All right? So we start outside of a word. We're in this state right now. We're in the outside of a word state. We see now first the space character. And so we remain in the outside of a word state. So we're still sitting in outside of a word. Then we see another space. Still outside of a word. Yeah? See another space. We got to follow a transition every time we see a character. But we're outside of a word. We see a space. We're still outside of a word. See how I'm reading that and following it? And then I see my H. I'm sitting in the outside of word state. I see an H. That's not a space character. So I don't follow this transition. I take it and I follow this transition and I go to the inside of word state. So now I'm in the inside of a word state. And I also, every time I follow this transition, I've promised to add 1 to my count. So I'm going to add 1 now. Counts 1. That's my first word that I've seen. All right, so I'm in the inside of word state. I just transitioned to there. And now I see my I character. I'm in this state. I see a non-space character. It's still part of that same word. I'm still inside of a word. Okay? But then when I see a space and I'm inside of a word, I'm going to go back to the outside of word state because now I'm in between words. All right? Any spaces are in between words. So now I'm sitting in the outside of word state. Are we following? And then I see an M. I'm in the outside of a word state. I saw an M, which is a non-space character. So I'm going to go and transition to the inside of a word state and add 1 to my count. So now count is 2. So I'm in the inside of a word state. I see the O, still a non-space character, stay inside of a word. See the M, still a non-space character, I'm inside of a word. See an exclamation point, still not a space, still inside of that word. You'll have to change the state machine if you're trying to count the words in a French sentence, because spaces, you put a space before the exclamation point in French. But English is cool. So we're still inside of a word, and then we see another space at the very end of all this. We see one last space, and that takes us from inside a word to outside of a word. And so we end up in the outside of word state, and our count is really what we wanted to care about. And our count has been set correctly to 2. Do you see how if you could code this up, if you could make this in Scratch, you would correctly always count the number of words in a sentence? Isn't that so cool? It's honestly pretty simple once you get used to state machines. And it is not obvious how you would code this up in some other way. This is like the way that it works. So this is essentially what Microsoft Word is doing or Google Docs is doing when you ask it to count words. It's running the state machine on the text of your essay. So yeah, that is a state machine. That's the coolest one. But they all got starting states, got transitions to move you around between the states, and you can have stuff happen on those transitions if you want to. That's how you can do cool stuff, and this is one thing that would make it into a program somewhere. Any last questions about any of that? So we talked about a lot today. Some cool new knowledge, a bunch of different areas, and yeah, I think that's all that I wanted to say. So I'll give you a new programming assignment, but we'll deal with that on Wednesday on the programming lecture day.